Thank you very much. So it's a true honor and a delight to be here. This is my first gathering for Gardner. I hope not my last. And I have found my tribe, right? You are all fantastic, wonderful people. Everyone's so interesting and fascinating. And everyone's got loads of different interests, as have I, right? So last night I talked, those of you who came, I talked about mathematics and literature. This is one of my real huge interests is the links. I'm a pure mathematician, I'm a group theorist, an algebraist. I'm fascinated by the links between mathematics and the other creative arts, whether that's music or literature, which I spoke about last night, or visual arts. We're all doing the same things. We're finding beauty. And in order to find beauty, what do we like? We like structure and pattern. We like symmetry. And so those things are present in music. They are present just inherently. And I'm going to talk about the Western classical tradition of music, but they're present in all forms of music in different ways. They're inherently there, so composers can't help themselves but have patterns and symmetries. But also, and we'll get onto this in the last bit of my talk, composers have deliberately used mathematical structures and objects in their composition, and we'll see some of those later on. So I'm aware, in this big group of people, there will be lots of different bits of knowledge here and there. Some of you know loads about music, some of you less, some of you are algebraists, and some of you aren't, right? So I'm just going to begin with a couple of minutes to set the ground rules for what I'm going to talk about in terms of music. So this is a piano keyboard, or part of one. We have the notes on the piano, and they have names. They are named for letters A, B, C, D, E, F, and G. And then you've got, so those are the white notes, and then the black notes are in between. And these are the notes we have to play with, the pitches. So when you're a mathematician, as I am, you get a bit anxious if two seemingly different things are given the same name. So what's going on there? You've got several notes here that seem to have the same names. I'll just play you, and you'll see why. Two of these notes that are called C, they sound very similar. There they are together. Level one. Right, when we sing, as we did a bit last night, sort of in unison, then we're not, in fact, all singing the same note. Even if we really are singing in unison, usually the men will be singing an octave lower than the women, right? They sound so similar that it's as if they're the same note. They are the same pitch class, we call it. We give them the same name. They're both a C, but one is an octave higher or lower than the other. So we talk about the register. So that's why we give those the same name, C. So you see all of these notes. Now, those two notes that we just heard, they are an octave apart. And in the octave, we divide the octave into 12 different pitches. And the shortest distance, the gap between any two adjacent ones, we call a semitone. Okay, so we divide it up into 12. There's a whole different discussion on how that's been done over the years. You need to know what the 12th root of 2 is. That's a subject for another lecture, not today. But once we've done this division, we have these 12 notes. And these are our 12 pitches. And that's how we make music. But not all notes are the same. Not all pitches are the same. So traditionally, you would write a piece of music, you would have a key signature. And this would involve the notes from a particular key. So the piano is biased. It's biased towards the key of C. The white notes, if you just play those, there aren't 12 of those in an octave. Let's hear what happens when you play that. Sorry if my piano is out of tune. Okay, that's the scale of C major. If you've ever learned a musical instrument, you will know this. Now, what we're hearing here is a pattern of gaps between the notes. They're not all equally spaced. We see those notes on the piano, between any white note, there might be a black note or not. Those small gaps, those black notes, are filling in semitones where there's a tone gap. So this pattern that we just heard, it goes from C to D, there's a black note in between, so actually from C to D is not a semitone, it's a whole tone. So we go tone, tone, semitone, tone, 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 semitone, okay? That pattern of intervals is what our ears are hearing. We can shift that up or down. We can start from any beginning point, but if we make that same pattern of intervals, of gaps, it sounds like the same sort of musical pattern to us. So that's the important thing. It's the gaps between the notes. And this, when you're going to do any kind of understanding of symmetries or mathematics, you need to know what you want to keep the same, what your invariant is going to be. In geometry, if you're doing Euclidean geometry, any kind of symmetry you do will preserve distance. right? When you're doing musical symmetries, you want to preserve intervals. So that's the basics. Now, it's quite useful to see some of these things visually as well. And so when we write music, we don't just write a sequence of letters. We use the stave notation, thanks to Guido d'Arezzo, an Italian monk some centuries back, who came up with this notation. And so we have these 5 lines, and these are our staves. And then we can put marks either between, we alternate either between 2 lines or on a line, and those give us our notes. What about the black notes that we haven't mentioned? Well, let's take maybe the one between the F and the G on the piano, if you're seeing there. That's a bit higher than F. It's a semitone above F. We call it F sharp. We use like this hash symbol. Or it's one semitone below G. So it's G flat. Now, I will not go into the technicalities of when you use which of those labels. Let's just say we can use them interchangeably and not worry about it. So with those 2 symbols, you can then write any note on the piano. You can write any note down. You can also do a bunch of other stuff. You can change your symbol, and that tells you how long the note lasts, and all sorts of other things I'm not going to talk about. We're going to talk about musical symmetries, which change the pitches of the notes, but we really always want to care about keeping the gaps the same. So if you've got a gap of a tone, you want, whatever you do to it, you want that gap to still be a tone when you're done. Okay, so let's think about the kind of symmetries we could have. If you've got a theme, if we're composing a piece of music, if we're Bach, we can take our basic theme and then we can do things to it. The simplest thing you can do to it is just to repeat it. We can think of that as being like a horizontal translation, if you want. So you just repeat the same theme exactly the same. So the example I'm showing you there is from a choral piece by Benjamin Britten, which is absolutely fantastic. And in this piece, you have 4 different voices, and they do exactly the same thing, but just slightly delayed. So it's a brilliant effect, but you're repeating. So you're just translating it and putting it down later on. Well, okay, you can translate horizontally. Maybe you can translate vertically. Yes, you can. I'll just call that translation, in fact. So you can take a theme or a motif, and you can do it, and then you can play it again, but a bit higher or lower. So you can go da-da-da-da, and then you can go da-da-da-da. Hopefully you recognize that with my brilliant singing. By the way, if my voice is a bit hoarse this morning, it's not because I gave a talk last night. It's because I spent 3 hours after the dinner last night gasping in awe. So that's what that is. I blame the magicians. Okay, so sorry about that. Okay, translations, fine. We can go across, we can go up and down. What other kinds of symmetries might we imagine? Well, we can reflect things in geometry. Can we reflect things musically? Yes, we can. That's called inversion. So here's a horizontal mirror, and we can reflect a theme. Here's a very simple one, because I'm a simple person. Playing your scales. Right, that's in one hand I'm going up and then down, and then in the other hand I'm going down and then up. Right, that's the end of the musical abilities that I have. But you can see this, you can see it visually, but we can really define it mathematically precisely, because with the visual thing, this stave notation, again, it's biased. It's biased towards the C major scale, because without using the sharp and flat symbols, you can't represent the black notes, the ones that aren't in the diatonic scale for C major. So it can look as if 2 notes that look adjacent in this notation may either be a tone or a semitone apart. So this is not perfectly accurate representation sort of for what we might do mathematically, but we can define it precisely. We can say, what's an inversion around a particular pitch? Well, you know, if you're 3 semitones above it beforehand, then afterwards you're 3 semitones below it. So we can define it precisely, but it's nice to have a visual image. So we can see this in loads of classical compositions. I mean, it's always Bach, right? So you can go and look at any piece by Bach and you'll find all of these things, I'm sure. Here is just the first 3 bars of a fugue of his, and there's a theme, and then that's in the right hand, and then a few bars later, you see it repeated in the left hand, but inverted. Okay, so you can play around with these things. Okay, well, that's reflection in a horizontal mirror. Of course, we can think about reflecting in a vertical mirror. That's obviously what we want to do next. That's called retrogression, or playing it backwards, if you don't want to use a fancy word. So again, loads of examples. I've just picked one out from a minuet by Haydn, and you can see that the second half of this minuet is the first half, but just reversed. And it even helpfully says al reverso in the score. And I've just put it all on one line to make it even more obvious, hopefully. So, okay, we've got these kind of symmetries. Now, if you think about geometry, if you like geometry and you know about the symmetries that shapes can have, they can have reflections and sometimes translations if it's, a wallpaper pattern or something. We haven't mentioned rotations yet. And that's a very common geometrical symmetry. Now, it's a bit tricky to think about what that would mean in music. Like, you can't really rotate a pitch. That's puzzling. But if you have a physical score, then you can talk about what happens if you rotate it. So that's some really cool examples. I encourage you to go on YouTube and find people playing this it's a duet here. This, Der Spiegel, confusingly called the mirror, even though it's rotated. Anyway, never mind. It's attributed to Mozart, but I think the attribution, there's a question mark, perhaps. But this is a duet for 2 violins. It's really brilliant. Go and find it and watch it. You stand opposite each other. You have the score in between you. So one of you is seeing what I'm showing you there, and then the other one is seeing the rotation, right? And you play it at the same time. And of course, the skill here is making it sound nice together when you do that. So this is like really fun thing to do and explore. So that is a way we can get rotation into this. But it doesn't do this thing, doesn't preserve the intervals. It doesn't keep the intervals the same. So that's in a kind of different category because it relies on the physical expression of the music to do that symmetry. So it's different, it's very interesting, but we're gonna kind of leave that to one side because it's not like the other things that you can define purely in terms of pitches. So those are some kinds of musical symmetries. And these just appear and are used by classical composers for hundreds of years. Right, great. But something happened at the start of the 20th century, after the First World War, this cataclysmic time in history, and across the arts, people wanted after that to sort of say, right, we're done with that. Let's find new things. Let's explore new ideas. The old stuff is broken. Let's just begin again. So there were composers, for example, Schoenberg, most famous example of this, who wanted to move away from the traditional key signatures. So traditionally, you write a piece of music, it's set in a particular key, the key of C major or D flat major or, I don't know, F sharp minor, whatever you want. And then you stick within that, and there are particular notes that are in that scale, like the C major scale I played you, that are emphasized more and have more of a role. Well, what I'm about to describe to you, this 12-tone method, totally democratizes that. All of the pitch classes appear equally often by design. There is no key signature. So the old 24 keys that you could use, 12 major and 12 minor for each of the 12 different pitch classes, that's gone. And so what do we replace it with, right? Because we are making music and not just noise, we need some kind of structure. Okay, that's what music is. So what you do is instead of your key signature, you define what's called a tone row. And this is a specified ordering which you give of the 12 different pitch classes. So remember, that means if the third note is going to be C, I just care about the pitch class, so I don't care which octave it's in. It could be higher or lower. I don't mind about that. It's just got to be a C of some kind, right? So that the register doesn't matter. High or low doesn't matter. So you order those pitch classes into a particular order that you decree, and that's defined for that piece of music. So then what do you do? Well, you don't just repeat that many, many times. You're allowed to transform this tone row, this row of 12 notes in a particular order. You can transform it with anything that preserves intervals, because that's what kind of gives you the flavor of that little motif, that musical theme. So this is what you're allowed to do, and then that gives you a bit more things to work with in your composition. So this is I've taken away anything that's like might confuse, durations, rests, anything like that. I've just given you the notes here, showing you the theme and then some of the transformations from the first composition of Schoenberg that is composed entirely with these tone rows. So the theme, that's what the starting point, and then you can transform it with some of the things we've seen. So you can play it backwards in retrograde, right? You can invert it, flip it in a horizontal mirror, and you can combine. You can do a retrograde inversion if you're feeling very spicy, and you can do that. So there's lots of different variants you can use. Now, I've said we're throwing away the old. Okay, we are, but there's a really cute little thing that happens hidden away in the retrograde theme here that Schoenberg does. So if you can read music, you kind of can get the joke straight away. So what are the notes we have here? Well, the first one is B flat. Now, actually, in the German tradition, you just call that B. And then a B that isn't flat, B natural, for reasons I don't understand, is labeled H. Now, that's what they call B flat and B natural, have these two names. So the first note is B flat, that's B. Then you've got an A, that's A. Then you've got a C, and then you've got a B natural, which is H. Bach. So there's this cute little, okay, we are trying new things, but we are not forgetting our, the wonderful composers that came before us, even though it's in retrograde, so, okay. So this is lovely to see. Bach is in the Schoenberg. We stand on the shoulders of giants, right? Okay, so important question. We've got these tone rows. Given your tone row, you can compose. You can modify it by transforming with any interval-preserving map or transformation. I say map sometimes because it's shorter a word than transformation. Okay, so then it really becomes important to know what are the interval-preserving maps. We can find some. How many? What are they? Let's try and understand them. And of course, mathematics is going to help us here. So I will let the composer Yannis Xenakis, who was, he was an engineer, an architect, he worked with Corbusier, and then he became a composer, so he's got a lot of mathematics, and he really enjoys both of these things. I'll let him say it for me. Music, what is it? A set of structures. It's very often a set of structures made from the permutations of notes and of sounds. Okay, music is steeped in the problem of symmetry. And symmetry is made accessible by the theory of groups. I'm a group theorist by training, so this is music to my ears. I can make a pun. So symmetry, every time you have a symmetry of any kind, you get these things, groups. So I know there's lots of people here who know all about groups. I'm not going to give you a lengthy disquisition on what groups are, but basically, just in case you don't know, a group is a set, but it's a set, it's active. It doesn't just sit there being a set. You can combine elements of the set. There's a way of combining pairs of elements, and the outcome is something else that's in the set. And so this is the kind of the first rule of a group. It's called the closure property, that there's a way, some way of combining things in the set to produce something else, and that still ends up in the set. There are 3 other rules. I'm not going to tell you. If you know, you know. If you don't know and you want me to tell you, I'll tell you later. Okay, groups are everywhere because the group is the natural structure of a symmetry. So anytime you have a shape and you want to know its symmetries, they form a group. How are we combining them? We just do one and then we do the next one. Composition of maps, right? So do your rotation, then you do your reflection. The outcome will be another symmetry. Okay, there's a few people in the room who may have a pack of cards. Shuffling cards, that's another group. You do a shuffle, you do another shuffle, the outcome is a perhaps more complicated shuffle. So I'm just saying, these are closed, these permutations of things. Another group. Numbers. How are we combining numbers? We can add them together. So if you have whole numbers, integers, if you add together any 2 whole numbers, the answer is another whole number. All of these are groups. Groups are everywhere. They are ubiquitous in mathematics and everywhere where you might have symmetries. And so, in music, all of these interval-preserving transformations, they form a group. So it's very, very cool. And you can see why at least the closure rule is going to be true, because if you keep all your intervals the same, and then you keep all your intervals the same again, well, the net effect is you've kept all your intervals the same. Okay, so it makes sense. So let's try and think about what our interval-preserving transformations might be. Let's go looking for some. And the closure property is really useful to us here because it says if we've got a bunch of these things, then it ought to be the case, and it is the case, that we can combine all of those things with each other and produce new interval-preserving maps, right, because of the closure rule. So let's think about what we've got. We've got translations. Now, I didn't want to kind of use the stave notation so much now because of this ambiguity. It's not quite right about, are we going up by a tone or a semitone? So I've sort of just done it like this. It looks a bit more like a graph. So a translation, right? You move up or down a certain number of semitones. So here I'm showing you what I call T2, translate up 2 semitones. You just take your whole theme, just move it up, that number of semitones. So if we combine translations, we can probably predict what we're going to get. Let's combine this. Let's now do T minus 3. So you can go down 3 semitones. And of course, if you do T2 and then T3, well, you've gone up to T2 and then T minus 3, sorry, you've gone up to, then you've gone down 3, so the net effect is you've gone down 1, right? So it's quite easy to think about how we can combine translations. You just get another translation. Okay, so great, we understand translations. How many different translations are there? So you could say infinitely many, and you'd be right, but in the context of tone rows, remember we said we don't care about the register of these notes. So if it's a C, we don't care which C. You can go up or down any number of octaves. We just care about the pitch class. So if you're thinking like that in the context of tone rows, actually, if you translated everything up by 12 semitones, there are 12 semitones in an octave. Okay? So we've gone up a whole octave. We've just moved the whole thing up an entire octave. We haven't changed any of the pitch classes. It's like we didn't do anything. So this is the same as translating, up or down by 0 semitones. So in algebra, we call this the identity map, right? You're not doing anything. You're leaving identity as in identical. Everything's just left where it is. That's one of the other things you need for a group, actually. You need to have some element that does nothing. It leaves everything fixed. So that tells us, this is kind of like the clock arithmetic group, right? There are 12 different translations. And actually, once we get back up to 12, we just start again from the beginning. So there are 12 translations. Okay, we've counted the translations. We're doing well. What about inversions? Is one of our other maps. So this is like reflecting in a horizontal mirror. And just like standard reflection, it matters where your mirror is. Okay? If you move your mirror, you're going to get a different outcome. So the same with inversions. And just like with translations, there are 12 inversions. If you can reflect about any pitch, you get 12 inversions. Actually, the reason there are 12 is slightly more complicated than what I've just said, but it boils down to the same thing. But there are 12 inversions. Now, we've got translations, we've got inversions. We're supposed to be able to combine any of these things with any other and get another symmetry. So what happens when you combine, let's say, inversions with each other? Well, I can show you visually. Let's do 2 inversions. So if we reflect, if we invert about this purple pitch, we'll get something like this. And then if we invert again, we'll get something like this. And that is the same as, it turns out, just translating up. And if you want to know exactly, you translate through twice the distance between the 2 mirrors. Okay? So 2 inversions gives you a translation. What about inversion and translation combined? Well, okay, let's do an inversion. Let's do a translation. And that turns out to be exactly the same as inversion in a different mirror. We move the mirror up a little bit. And so that's the net effect. So we can see this closure rule is happening. The inversions and the translations already are giving you, well, it's okay, it's a dihedral group, if you know what that means. You're getting this closure property happening just with the inversions and translations already. So there's 24 of those so far. And there's another kind of map that we've already mentioned, retrogression, doing it backwards. You can combine that with any one of these 24 things, and you get, and any mixture of any of these things will result in one of the 12 translations, one of the 12 inversions, one of the 12, we call them retrogressions still if you combine with the translation, and one of 12 retrograde inversions. So this is great, and it turns out, it's not instantly obvious, but it turns out this is it. These 48 things constitute the complete set of interval-preserving maps. That is our musical group that we can use to work with these tone rows. So that's great. So now we know we can think of a tone row, we can use all these transformations, use the musical group on it, and we can get all these kind of images, and that's our basic color palette for our composition, okay? So, easy question, how many tone rows are there? Okay, how many different tone rows? Well, okay, you could say, well, there's 12 choices for the first pitch, 11 choices for the next one, and so on, right? That gives you a big number. Roughly 479 million. I won't give the exact number because I've forgotten it. But that's a lot. However, that's not really that's the wrong question. I want to know how many different color palettes I have for my composition. And what I mean by that is, we can transform, we're allowed to transform this tone row that we start off with any of the 48 musical symmetries. So potentially, we're going to get all of these images that are really, we could have used them as our starting point. And so, okay, you could say, well, all right, divide 479 million by 48. That's how many different, we might call them tone row classes or something like that. That's what we're really interested in. But there's an issue, there's a problem with this. Here's the problem. I know this isn't a full tone row, but it's a string of notes, okay? We do take this string of notes. Now, you can play it backwards, retrograde, and you get the thing on the right. But you also get the thing on the right if you invert it about the central note. That is the problem, because that means you've got two of these symmetries that take you to the same place. So you do not have 48 things in this collection of the same tone row. You have fewer. It's probably 24. I haven't checked. So that's a real issue, because now you can't just divide by 48. It looks as if you're going to have to go through all of these 479 million tone rows and work out who they're friends with, and that's not a calculation anyone wants to do. However, remember, these symmetries form a group, and that's brilliant, because group theory is one of the most powerful and fantastic things in mathematics. It's the best thing in mathematics. There you go, I've said it. It's the best thing in mathematics. You know it's true. So we have the whole power of group theory instantly at our disposal. And this is true. If you find a group in anything you're working with, instantly you've got all of your group theory that you can apply to this situation. It's like coming to this conference for me. Like instantly I might be thinking about something on my own, and then I find that I have 250 friends who can help me with this question, right? It's fantastic. So group theory does this for us, okay? There is a result in group theory which immediately solves this problem with just a few little calculations. And there's lots of different names for it. In England, anyway, we often call it the orbit counting lemma. I won't go into the detail, but basically, all you need to do here is you work through not 479 million things. You work through just the 48 elements of your musical symmetry group, and you work out how many tone rows they leave fixed. So that thing, I know it's not a full tone row, but that example there on the left, if we did retrogression and inversion, can't do that with my hands. If we did retrogression and inversion, it leaves it the same. So retrograde inversion would leave that motif looking the same. So we can do a little quite quick calculation to check for each of the 48 elements how many things they're going to leave fixed. And then we kind of average that out over the group. And that will give us an answer. It's a lot, but it's not 479 million. 9,985,120, okay? So that's how many tone rows we've got. That's more than 24. So well done, Schoenberg. He's given a lot of things to play with. Now this is one real use of group theory in music to say, here is what you can do. Here are the possibilities. Fantastic. There are lots and lots of composers who have used ideas from group theory, ideas from set theory to develop compositions. Lots of them. Milton Babbitt, for example, go and look up some of his work. There's actually a Babbitt's theorem, which is great. That's your homework. You can go and play around with these ideas. So once you've got the concept of tone rows, you know what to do, you've got these images, you've got the musical symmetry group. Some composers then took these ideas and they took them perhaps to the extreme. And this is called total serialism. So Pierre Boulez wrote a piece of music for two pianos. It's called Structures in 1952. He had his tone row. He had all its images, and actually there were 48 images of it. It was an example of a tone row which wasn't fixed by lots of things, or indeed anything. So it had 48 images, and he used it not just to define the pitches that would be played, but the durations of the notes, the dynamics, so how loud or soft, every aspect of the music. He processed these things. He had some matrices, and he did some stuff. Now this, it's very interesting, because when you listen to this, it's this kind of circle effect, right? There's so much structure that it's almost like it's random. It's weird. Because he's not controlling any aspect of it himself. He's kind of programming it through, and so he's sort of forced to do certain things. And I mean, this is like is it the apotheosis or is it the nadir? You can decide. But when he was asked about this later, so this is the 50s, is after another cataclysm that happened, the Second World War, and he said, look, this is kind of a way to give ourselves a blank slate. He made everything be a process. He said, so this is a quote from him, had computers existed at the time, well, maybe they did, I would have put the data through them and made the piece that way. But I did it by hand, did it all by hand. He was his own computer. And then he says it was a demonstration through the absurd, right? He took it to the absolute limits, the extremes, And then, you pull back from that and decide where you want to be. And this is a wonderful, stimulating continuum between complete freedom and complete constraint. Somewhere in there's the happy medium of maximum creativity. This is what we all sort of are exploring. So this is Boulez. Someone said to him, do you like listening to structures? He said, I don't feel any need to listen to it anymore. So yeah, there we go. Well, that's sort of, he's gone right to the extreme. I want to, in the kind of the rest of this talk, show you, these are structures that arise naturally in music that, composers were using without necessarily thinking about groups or anything else. I want to show you just 3 examples of mathematical ideas or structures that composers have consciously incorporated into their music in the kind of the 20th century and beyond. So the first one, this might be my favorite one, magic squares. Okay, obviously I'm putting my favorite magic square to illustrate the concept. You all know what a magic square is. The British composer Peter Maxwell Davies used magic squares in his composition. And several of his pieces, he did this thing which he called processing through a magic square. So he would take a theme, a motif. In one case, it was a Gregorian chant, piece of ancient music, with an 8-note motif, and he processed it in a way I'll describe through an 8x8 magic square. The magic square of Mercury, he called it. So I'm going to show you this idea, but I didn't want to have such a huge square. So I thought, okay, I'll use my favorite magic square, Dürer's magic square. Probably not invented by Dürer, but anyway. Dürer's magic square. And then, so in order to do this, I'm going to need a musical motif. It has to be the same size as the square, right? So I need a musical motif that has 4 notes. So I decided, okay, I know. Of course, I'm going to use the Bach motif. So this is my Bach process through Dürer. If you want to, if you have more musical skills than me, if you want to use what comes out of this as the grounds for a wonderful musical composition, be my guest. But I was just to show you the idea. So you take a square, 4x4 square, and you put your motif, your theme, along the top row. So that's Bach along the top row. Okay, B flat, A, C, B. Then, in each subsequent row, you are going to translate that motif up or down by a prescribed amount. In the nth row, you translate it so that the first note in the nth row equals the nth note of the original theme. Okay, so in the second row, you will see we've translated it so that, we've translated it down, I guess just one semitone probably, we've translated it so that the first note on the second row is the same as the second note in the original theme. Okay, so you do that, and you get a square. This gives you a mapping from those 16 notes we've produced to the numbers 1 to 16. Okay, so we've got that. Then we process it through our magic square. So here's the magic square of Dürer, and you can see the first row is 16, 3, 2, 13. And so you can, by the way, I thought this would be particularly appropriate because in the middle of the bottom row, it's got a 15 and 14, the wrong way round. Anyway, so this tells you the order in which to play those notes. So you play the 16th note first, then the third, then the second, then the third, and you work through the square. And here is the amazing, Bach through Dürer theme that we now have. And that can then be the basis of your composition. And these are all like, they help you, they inspire you with ideas, right? You have a structure, you make patterns to help you then just play and explore. So this is what Peter Maxwell Davies did with a bigger magic square and obviously a much bigger kind of theme. And it just gives you something to then as a starting point. And composers have always done this. There's an old technique where you take a saying, perhaps a psalm, and the vowel sounds that you have in that psalm, they correspond with the kind of do, re, mi, those vowel sounds that used to be ut instead of do. And then you work out which notes there are. So these kinds of techniques are not new, but doing it through a magic square I thought was a particularly cute idea. Okay, so that was number 1, piece of mathematical structure that we can use. Number 2, again, just one example really, but fractal music. So I'm showing you here Kaya Sariaho, brilliant composer, sadly died last year, I think. So in her work, she would often use fractal sequences. So fractal music generators use fractal sequences to create sequences of numbers that can then be used however you like in your music. So they can generate pitches for you. They can tell you what durations notes should have. They can tell you the speed, the dynamics, anything you like, that you can assign a number to, which of course is everything, you can run through and you can produce a fractal sequence to define the lengths or the pitches or whatever. So, I mean, we all know what fractals are, but perhaps we may not be so familiar with fractal sequences. We tend to think of, pictures when we think of fractals. I just wanted to show you one, which is so cool. It's just so cool. Okay, so you start off with the numbers in binary, and then that isn't the fractal sequence yet. Then what you do is you make a sequence from that, which is the sums of the digits in those terms. All right, so there. So 1, of course, the digit sum is 1. 1, 0, still 1. But 1, 1, digit sum is 2. And on you go. Now, some people prefer to do then a next step, which is to all of the even numbers in this sequence become zeros, all the odd numbers become ones. You can do that if you like. This one already, though, is still already a fractal sequence. And how do I know, why am I saying it's a fractal sequence? Well, what the fractals have, they have this self-similarity at different scales. If you pick out just the even number terms of this sequence, I'm highlighting them there, and then just pull them out and look what you've got. Same sequence being produced. It's really nice. And of course, within that subsequence, you can do the same trick, and you can get it again on a smaller and smaller scale. So this sequence contains itself infinitely many times at infinitely many scales. So if you use this to define, the speed at which your melody is played or something, you get the melody appearing, reappearing, coming backwards and forwards at different scales throughout the piece. So it's just a really interesting effect, and I encourage you to go and listen to some of her work. So that's fractals, and there's so many other ways in which we could talk about fractal music. I know Martin Gardner wrote about it as well. Okay, so fractals, logic squares. We're going to finish. The last example is really, again, could be a whole cluster of examples, but it's the use of probability and randomness in music. So Yannis Xenakis, who we met earlier, he created lots of music. He called it stochastic music, and he used things like probability distributions in his work. So how do you use a probability distribution in a piece of composition? So in this example, he used a Poisson distribution, just one of the probability distributions. It tends to model kind of rare events. And it tells you, if you kind of measure over time and you know the average number of events that occur per unit time, whatever that is, a second, an hour, a day, is whatever it is, lambda, then this is the expression that tells you the probability that actually in a particular time the event's going to happen k times, more than one time. So, what's the probability that if my kids on average have one completely pointless argument every day, what's the probability that today they're going to have 3 completely pointless arguments? We can work that out. It will happen annoyingly often. Okay, so here we are. Here's how the Poisson distribution fits together. So how does Xenakis use it in his music? So he's writing this piece of music. What are the events that are going to be happening? Well, okay, this is artistic. He calls them clouds of sound. So I don't entirely know what a cloud of sound is, but that's what the event is. A noise is made, okay? A cloud of sound happens. And he's using the Poisson distribution to say which bits of, how often these things will happen more than once in a particular part of the composition. So he's got his cloud of sound, and he divides up the total duration of the piece into 28 units of time, and then there are 7 instruments. So there's 196 what he calls cells, into which each of which can have 0 or 1 or more of these clouds of sound. Okay, and you've got to set your parameters. So he set lambda to be 0.6, which is kind of gave the right sort of amount of sound versus silence, which you can't have all sound all the time. So he set this parameter after some experimentation. And then how do you work this? So for instance, he says, okay, we can calculate P2. So that's the probability that you'll have an event, a cloud of sound, twice in a particular cell. So you can work that out. You plug it into the formula. You get 0.0988 roughly. And you've got 196 cells. So in 196 times that number, which is about 19, in 19 of these cells, there are 2 events. That's how he's using this distribution. He says it's going to be exactly this distribution. So in 19 of the cells, there'll be an instrument playing twice, 2 notes. So that's how he's sort of precisely laid out the parameters for this piece of music, and then within that, of course, he gets a lot of choice still to be creative. And I think that's what I want to finish by saying, really, is that all of these constraints and these wonderful mathematical patterns and structures and things that we can use, fractals, magic squares, they are there to help us be creative. They spur our creativity. They give us a framework to explore. And Xenakis did many other really interesting things. If you look at, you can see his architectural training, you see he worked with Corbusier. If you look at some of his scores, I mean, look at the geometry in this, right? It's very cool. And so there's mathematics just everywhere, and he's consciously doing this. These are glissandi, one of his other pieces. You use the mathematics, as Schoenberg said, my pieces are 12-tone compositions. They are not 12-tone compositions, right? It's the composition, it's the music is the thing. And the mathematics can help you get there. So thank you very much.